Safe reinforcement learning-based motion planning for functional mobile robots suffering uncontrollable mobile robots. An increasing number of autonomous mobile robots, AMRs, have been used in warehouses in recent years. The risk of one of the AMRs being out of control resulting from software failure, hardware damage, or hijack is surging. An uncontrollable AMR may perform aggressive behaviors or even rushes toward other AMRs, leading to disturbances on the other AMRs, collisions of AMRs, and even the failure of the operation of a warehouse. A motion planning approach that can provide safety guarantees for the remaining functional AMRs and maintain the operation of the warehouse when an AMR is out of control is preferred. This study uses the model information of an agent or a small number of agents to achieve decentralized low-level control barrier function-based shields for the agents of multi-agent reinforcement learning. A multi-agent reinforcement learning with control barrier function-based shields algorithm is established to address complex high-level tasks, example, cooperation of a large number of AMRs, by multi-agent reinforcement learning and deal with the safety issues of every single agent, example, a functional AMR suffering a pursuer-like uncontrollable AMR, by a low-level control barrier function-based shield. To enhance the safety of functional AMRs, low-level CBF-based shields provide safety guarantees for functional AMRs even in the worst case an uncontrollable AMR pursues a functional AMR following the optimal pursuit strategy. Experiments are conducted based on an environment that simulates a warehouse both in a virtual environment and in the real world to demonstrate the multi-agent reinforcement learning with control barrier function-based shields algorithm. The AMRs are required to transport goods from one location to another. An AMR is assumed to be hijacked and pursues the nearest functional AMR. 3 reinforcement learning-based motion planning policies, a policy with shields, a policy without shields, and a policy with dynamic obstacle avoidance, are achieved for functional AMRs based on an environment consisting of 2 functional AMRs and 1 uncontrollable AMR. A policy with shields is achieved according to the proposed multi-agent reinforcement learning with control barrier function-based shields algorithm. A policy without shields removes the control barrier function-based shields from the policy with shields. A policy with dynamic obstacle avoidance regards the uncontrollable AMR as a dynamic obstacle and addresses the dynamic obstacle based on reinforcement learning according to references. The average total rewards achieved by the functional AMRs following 3 motion planning policies in training are presented in the figure. Firstly, tests are conducted in a virtual environment involving 2 functional AMRs and a pursuer-like uncontrollable AMR. A video of a test of 2 functional AMRs that do not suffer time delay and disturbance and 1 uncontrollable AMR is presented. It is shown that the 2 functional AMRs following the policy with shields can travel between the initial position of goods and the target position of goods and avoid collisions when the uncontrollable AMR is pursuing one of the functional AMR. Tests involving 2 functional AMRs and a pursuer-like uncontrollable AMR are conducted in the real world also. A video of a test of 2 functional AMRs that do not suffer time delay and disturbance and 1 uncontrollable AMR is presented. One can see that the 2 functional AMRs following the policy with shields can travel between the initial position of goods and the target position of goods and avoid collisions when the uncontrollable AMR is pursuing one of the functional AMR. To evaluate the scalability of the policy with shields, tests are conducted based on a scale-up virtual environment that includes 10 AMRs. 2 of the 10 AMRs are uncontrollable. The uncontrollable AMRs work as aggressive pursuers following the optimal pursuit strategy. To scale up the policy with shields, an actor network with a CBF-based shield is randomly selected from the 2 agents of the achieved policy with shields and applied to the 8 functional AMRs. A video of a test of 8 functional AMRs that do not suffer time delay and disturbance and 2 uncontrollable AMRs is presented. One can see that the 8 functional AMRs following the policy with shields can travel between initial positions of goods and target positions of goods and avoid collisions when the 2 uncontrollable AMRs are pursuing the functional AMRs. Thank you for watching.